Kumar. Professor Kumar is at the forefront of advanced research as the leader of the Collaboratory for Algorithmic Techniques and in Artificial Intelligence at the Information Sciences Institute of the University of Southern Carolina. He holds multiple appointments at USC, serving as a research associate professor in the Department of Computer Science, the Department of Physics and Astronomy, and the Department of Industrial and Systems Engineering. His academic contributions are vast, with over 160 papers spanning a wide array of subjects, including constraint reasoning, machine learning, robotics, combinatorial optimization, and spatiotemporal reasoning, among others. His work has earned him 3 Best Paper Awards and has greatly influenced both academia and industry. Professor Kumar has also provided his expertise to leading companies, including Meta and Avalon. His academic journey includes a PhD from Stanford University. Most importantly, he did BTech from IIT Guwahati, class of 1999. And with past roles that have taken him to NASA Ames Research Center, UC Berkeley, and other prestigious institutions. Please join me in welcoming Professor Satish Kumar, a true pioneer in the fields of artificial intelligence and computational science. Welcome, Professor Satish Kumar, to this wonderful webinar.
Thank you so much.
This was just a formal introduction, but informally introducing Professor Satish Kumar is an absolutely amazing conversationalist. You'd be amazed as how you'd be really amazed through this entire session. The way in which he has defined the heading, building blocks and architectures, algorithms, AI, and beyond, that itself shows the foundational aspect of how he looks at the world, how he looks at applications, how he looks at research in general. And I'm sure that all of you have joined us from various, various spaces, whether you're a student, whether you're working, whether you're planning to go for more higher education, all of you would have specific takeaways from this session. So thank you for joining, and let me just hand it over to Professor Satish Kumar.
Thank you so much, Rahul. That was great. I just wanted to mention that I'm actually from the first batch of IIT Guwahati. So it's a real pleasure to be seeing so many of our juniors in this forum today. So the other thing is about my last name, which is obviously very long. The correct pronunciation is Tittamarnahalli. And it's also a giveaway for where I could be from, right? And if you're still wondering, I'm basically from the blessed state of Karnataka. So having said this, I'm going to tell you what my agenda is for today. So very briefly, I will introduce my lab at the University of Southern California. And the pronunciation for it is CATI. It's an acronym, right? That stands for the Collaboratory for Algorithmic Techniques and Artificial Intelligence. I will tell you in a minute why it is the way it is. And after that, we'll go through 2 exemplary projects, right? There are plenty of things that we work on, but just 2 exemplary ones: multi-robot coordination and another thing called FastMap, right? After that, I will take a brief moment to put things in perspective about how to view algorithms and AI from a combinatorics perspective and what exactly is the relationship between them. And we will do a case study in nanoscience once we understand this different perspective. And the most important part of this talk is actually the last part about higher education and research, because that's about you, right? I mean, whoever is aspiring to do a successful PhD or wants to become a successful researcher, this part is really for you. Now, I wish I could have put this up front, right? But the thing is, there's a dependency here, because the first part of my talk, I think, will provide a testimony to the second part of my talk, right? So having said that, please bear with me until I cover a few of these topics, and then the grand picture will emerge. And also, one more thing to say here is that I know that it's going to be very tempting to ask very domain-specific questions, because we will go through a lot of these applications. But I also want you to understand that this is really not about the fruits of the tree. This is about the tree, which means the algorithmic techniques that go behind it, right? So if you have very domain-specific questions, I'm happy to take them offline. You can always write to me. But if you have questions about the combinatorial principles of what's enabling these things, then yes, we should certainly ask them. I will also make pauses here. For example, I will pause after multi-robot coordination once and poll for questions. Similarly, after FastMap, I will poll for questions, and then finally, of course, at the end we will have a question answering session where I think we are expecting quite a few questions once I go through how to do a successful PhD and how to be a successful researcher, because I think that'll get you interested. All right. So also the chat window is open. So I don't know. I mean, since I'm going to be pausing for questions anyway, we could just do that instead of using the chat. So, all right. So let me take you to the next slide, which is a little delve into my lab, right? And because the acronym for this is CATAI, and it's a good way to pronounce it as a cat eye, the symbol of this is also literally a cat's eye. It is an interdisciplinary lab at USC's Information Sciences Institute. The reason I call it interdisciplinary is that because we're really in the business of using principled algorithmic techniques, right? I mean, the keyword here is principled for solving optimization problems in AI. And we have plenty of very good success stories here, and I'm happy to share some of them here. And CATI also collaborates and shares students with another lab at USC called the Intelligent Decision Making Lab, led by Professor Sven Koenig, who is a longtime collaborator and friend of mine. And so at the ground level, really what happens is that we end up code-wising each other's students and everything. So it's really sort of hard to separate out like, who exactly is my student and who exactly is his student. But he's an amazing person, by the way, I must tell that also very prolific researcher. So in any case, among the 60 plus students that I have advised, code-wised, or partially advised, there are some statistics that I've gathered here. 23 doctoral students, and then 3 awards related to their PhD dissertations. And some of them have gone on to become faculty members themselves in very prestigious places, including Carnegie Mellon University, Simon Fraser University, Technical University Berlin, and some of them have gone to the industry as research scientists, including Meta, Muin Corp, and so forth. 23 master's students. Master's students at USC don't necessarily produce a thesis or dissertation, so their awards are different. But we have 3 awards related to their best research. And now, of course, they're at various places, including Amazon, Microsoft, NVIDIA, all these standard places. And then 16 undergraduate students, 5 awards related to their best research. And now also either doing PhDs in various other schools or joining software companies such as Google, right? So this is roughly what the statistics of our lab looks like. All right, give me 1 second here. Give me 1 second, please. Okay, so my research interests, now there are a lot of these topics that I have published in and continue to work in, right? I mean, I'm just going to go through this list real quickly. Machine learning and data informatics, combinatorial optimization, approximation randomization techniques, algorithms, complexity theory, constraint satisfaction, probabilistic reasoning, automated planning and scheduling, heuristic search, computational physics, hybrid systems, robotics, warehouse operations, multi-agent and multi-robot systems, operations research, supply chains, network resource management, model-based reasoning, knowledge graphs, and geometric and spatiotemporal reasoning. Now, the thing is that many people actually think that I am a domain expert in all of these domains. That's not really the case. The only real investment I have made is I have invested in algorithms and combinatorics. And once you do that, then you see every domain offers some sort of combinatorics, right? So if you're good at algorithm design, essentially you can start contributing after spending a reasonable amount of time and effort in picking up the language of that domain, right? And the problems that are of interest to that domain. So this talk is also going to be in the same vein as to how to become successful in multiple domains by being good in algorithm design, right? This is essentially the message of this talk. All right. So let me start with the two exemplary projects. So first one is about multi-robot coordination. I'm going to start by showing you a video, actually. Give me 1 second. Actually, I will start with showing you 2 videos, but you might have seen something similar, but this is just for those who haven't seen it and as a refresher for those who have already seen these kinds of things. All right.
The armed robots deliver shelves of inventory to pick stations. The laser points at the items to pick. The screen tells me how many. Quick scan to confirm, and a bin light indicates which order to put them in.
The magic shelf isn't real, but the Kiva mobile fulfillment system is. This order picker has crossed over to a better way to pick, pack, and ship orders. The Kiva system uses autonomous mobile robots to bring movable shelves containing merchandise to the picker, who stays in an ergonomically designed station to fulfill orders. The system is 2 to 4 times more productive than other pick methods, extremely accurate, and exponentially more flexible than traditional automation. Staples, Walgreens, Zappos.com, and other leading companies couldn't find a magic shelf, so they installed a Kiva system. You can too. Unless, of course, you actually have a magic shelf.
All right, moving on to the next one.
We have stored things in shelves forever. It's natural to us. We want things to be within an arm's reach. Robots, on the other hand, shouldn't have to. They shouldn't need rows of shelves or long walkways. So why waste time on shelf-based solutions when AutoStore is here? AutoStore is a cube-based system, making use of all space for proper warehousing. Turn that wasteful layer into storage and double, triple, or even quadruple the inventory capacity without moving to a new building. Bins are stacked right next to each other, on top of each other. Radio-controlled robots drive on tracks above the cube, lifts down to grab bins and deliver them to workstations for order fulfillment or replenishment. All operations get done efficiently and accurately in high-speed workstations. To get to a lower bin in the cube, the robot digs out the bin systematically. Every bin delivered to the workstations will be placed back on the top, making slow-running products to sink to the bottom and high runners to stay on top. With this natural slotting, digging becomes a minimum, resulting in high-speed operations. Your building can be of any shape. All we need is a flat floor. The cube can be constructed around columns, and oddly shaped rooms get properly utilized. If higher performance is needed, you can add more robots. If more storage is needed, we can expand your system without stopping current operations. Easy grid construction makes expansion fast and affordable. Build for today, expand tomorrow. AutoStore will never have a sick day. Even if a robot gets ill, the system will continue to deliver. It is a modular system, a flexible system you can trust. 10 robots use the same energy as 1 vacuum cleaner. Flick off lights and save that electric bill. AutoStore is being used all over the world in a great variety of industries. It is a high-quality product developed and produced by Norwegian technology company Hadeland, with over 40 years of experience with innovative technology. We have standard modules, but no standard system designs. Every system is thoroughly designed and simulated for performance and capacity before installation. AutoStore can connect to all warehouse management systems and will interact with other warehouse modules. Any robot can get any bin. Any bin can be delivered to any workstation. Your goods are still within an arm's reach. All of it. Stop air housing. Start warehousing. AutoStore, a product by Hadelin.
All right. Let's come back to the presentation here. Okay, so I hope that impresses upon all of you that, in many ways, the future of automation is teams of coordinating robots, and not just in the warehouse operations that you saw, but also, they're already being used in smart ports, manufacturing, drone delivery, connected autonomous vehicles, and so forth. So there is also slowly a paradigm shift that is coming in robotics, as you might have noticed. In the past, the investment used to be in sort of these big robots with lots of functionality, but high precision robots. But now the paradigm is one of investing in teams of robots, small robots, cheap ones. Some of them are so cheap that you can even 3D print them, like Harvard has some of these robots. And you want to let them coordinate, accomplishing various kinds of tasks, right? So what is the benefit of going with teams of small robots as opposed to few larger robots? Well, one is the cost benefits, obviously, right? I mean, I just argued for how cheap some of these smaller robots are. The second benefit is one of robustness, right? I mean, if a large robot fails for some reason, there is no recovering it with ease, right? I mean, a lot of dollars go down the drain. Whereas in teams of smaller robots, what happens is that one robot fails, fine, the rest of the team will cover for the failed robot, right? I mean, so that's both in terms of cost effectiveness as well as in terms of robustness, it's a good idea to deal with teams of smaller robots. Now, having said this, there is going to be a secondary problem introduced because of, I mean, we have to pay something for this, and that is the task of coordination. For example, in the warehouse domain that you saw in Amazon and Kiva Systems, right? Yes, we want to let the robots run around and fetch the inventory pods and so forth to the picking stations. But the secondary problem introduced here is that, the robots cannot be running into each other, right? I mean, so they cannot be deadlocking with each other. And, what if one robot fails and blocks an alleyway and all kinds of issues come up. And we don't want to be in the business of controlling or issuing commands to every single robot. We want to be able to issue very high-level commands to the team as a whole and let them figure it out, right? I mean, as to how each one is going to split the overall task and coordinate with the rest of the team so that the overall task is accomplished, right? So this is where AI comes in to help robotics folks, right, in this coordination aspects. All right, so so in 2018, actually, we won a technology commercialization award for the use of our algorithms in these fulfillment centers, right? And a lot of this work goes under the keyword of multi-agent pathfinding, and I'll tell you what that is in a minute. But before actually, you know what, I'm going to show you a little video that shows how I mean, this is actually from our lab, how we can command a team of drones to go and spell the word USC in midair, right? I mean, without actually commanding any individual drone, right? Just as a team, you give a high-level command. And so the drones will figure it out as to which one goes where, and then how to avoid conflicts with, how to avoid collisions with the obstacles in the environment. And you will see that the environment, once I play the video, you will see that the environment is actually full of obstacles, purposefully placed. So they have to avoid collisions with the obstacles, collisions with themselves, I mean, between themselves, right? I mean, so no two drones can be colliding with each other, as well as when it comes to drones, the matter is a little bit more complicated because they're fighting gravity as opposed to the land robots, as opposed to the ground robots, right? So any amount of time that you spend on just planning and deliberation actually is going to be counterproductive because you'll start falling down, right? Because you're fighting gravity. The other issue that comes up is because the quadrotors in the drones have fans on them, namely the blades, right, that sort of lift them. One drone cannot be directly above the other one because it creates a sort of a downwash on the other one, right? And it destabilizes it. So all these issues are going on, right? When one of downwash, one of fighting gravity, the other of avoiding collisions with the environment, avoiding collisions between each other, and yet accomplishing the high level task as a team and doing it in the most efficient way. So it sounds like a very complex problem. Let me tell you how to solve this. So this, when I go through this aspect of this project, I'm going to show you how to look at this problem at various levels. But let me first show you the video and show you what it looks like. All right, so please, once I start this, please pay attention to the very first part of it, because that's what the exciting part is, right? All right. So if you're all ready, I'm going to play it now. All right, so I'm going to pause it here just so that you can notice that we have actually spelled the letters USC, right? I don't know whether it's clearly visible, but that was the goal of this task. So anyway, the rest of this video is about the techniques, which I'm happy to play after we cover some of the techniques behind this. So let's get back to my presentation, and I'll start telling you about what kinds of techniques go behind this. All right. Okay, so before I tell you what these techniques look like, there is one principle that I want to mention, right? So suppose I tell you that there are 8 birds sitting in a line and then 2 of them flew away. How many remain? Well, I mean, clearly the answer is 6. But it would be crazy if you came back and told me that, you will never find 8 red parrots sitting in a line, right? That's not the point, right? I mean, the point is that it's the principle that's important, right? I mean, so I'm sure you have used addition and subtraction in many real world situations, although it was first given to you in very toyish situations, right? So in the same way, there are a complex real world problem looks very different at different levels of abstraction. All right. So there might be certain levels of abstraction of the problem which look very toyish because we are making a certain bunch of assumptions which are not really realistic. It looks like, okay, what's going on here, because all these assumptions don't work in real life. But that's not the point. The point is that might very well be the abstraction level in which the heavy lifting of the combinatorics is being done. I'm happy to reinstate the realistic aspects of the world later on, but let's do it one abstraction level at a time. All right, because in this complex problem, for example, the problem appears very different from a complexity theory perspective, very different from an AI perspective, different from a robotics perspective, and different from a physics perspective. So it's important. So part of the art in solving complex real world problems is the ability to peel the complexities of that problem in the right order. All right. So, okay. So having said this, please keep this in mind. So having said this, I'm going to first show you what the problem looks like from a complexity theory perspective. All right. So from a complexity theory perspective, the multi-agent pathfinding problem is just this, right? So we are given a graph. Let's first study it in a graph, right? So we are given a graph, an undirected graph like this, and all of us know the single agent shortest path problem, right? I mean, so we have some, let's say there was only one agent, agent one, and there was some start location for it, S1, and some goal location for him, let's say T1 or something. We know how to solve the shortest path problem on graphs. I mean, this is polynomial time solvable using Dijkstra's algorithm, let's say, since it's an unweighted graph. But when there are multiple agents involved, right, then the problem becomes a little bit tricky. So even if we, so first of all, in graph theoretic terms, we are making a whole bunch of assumptions. We are calling the robots as agents because, you know, we need to abstract several things about the problem into certain simplifications. So edges, for example, have unit lengths, right? It's okay to make that assumption for now. And then agents have uniform velocities, which means that they're going to jump, it's going to traverse from one vertex to another neighboring vertex, right, via an edge, right? And it's going to take unit amount of time, and the velocities are uniform. And then there's perfect plan execution, meaning that, you know, once you try to execute something according to your plan, it always works, right? And then there's a notion of discrete time. It's logical time. It's not continuous time. Right. Notice that, you know, in the real world, none of these assumptions hold. I mean, obviously, in a layout like this, so different edges might have different lengths, right? And then there are kinodynamic constraints in the robot. So agents, these are robots with real kinodynamic constraints. So they don't necessarily have uniform velocities. They have different acceleration capabilities and so forth. And there are always imperfections in plan execution. You might think that you're going one way, but, you know, there could be a certain amount of error or accumulation of drift, and you could be headed in a slightly different way, right? I mean, so all these could accumulate. And of course, we are in the real world, so we need a notion of continuous time, right? But the point is that we still want to study it in graph theory for the same principal reason that we first want to do the heavy lifting of the combinatorics here. So the multi-agent pathfinding problem on the graph theoretic terms is now a generalization of the single agent pathfinding problem, where there are multiple agents, right? I mean, so S1 sitting here starts from here, needs to get to the target location T1. So agent 2 starts from S2, needs to get to T2, and so forth, right? So different agents have their corresponding source and destination vertices. And the constraints of the problem is that every agent can move, traverse one edge in one unit of time. If he chooses, he can wait in the vertex that is already in, but he can also traverse one edge at a time, right? And they have to avoid conflicts with each other. Obviously, every agent needs to get to his destination, but they also want to avoid conflicts with each other, which means at any given point of time, no two agents should be sitting in the same vertex, right? Should approach the same vertex. So that's a vertex collision that you want to avoid. And then the second thing that you want to avoid is no two agents that are sitting on opposite endpoints of an edge. They cannot exchange locations in unit amount of time, because presumably these edges are representative of narrow corridors. So two agents cannot swap locations in the same unit of time, right? So we want to avoid edge conflicts as well. So under these constraints, where we avoid vertex conflicts as well as edge conflicts, then the problem, unfortunately, is no more polynomial time. It's an NP-hard problem. All right. So you want to minimize any reasonable metric, let's say the make span, where all the agents go and achieve the target locations, or the sum of the distances covered by all the agents, or for all these interesting objectives, the problem is NP-hard, unfortunately, right? So it's good to know this, that because, you know, despite all of these assumptions, the problem is hard, right? So okay, so the complexity theory guy is basically done with analyzing this problem. We are up against a negative result already, right? What can we do about it? So, well, this is where the AI guys come in. We want to salvage the combinatorics of this problem, although the theoretician declared it to be an NP-hard problem, right? We want to develop a practically good solution for this, right? How do we do this? So this is the idea of conflict-based search. So it's once again, I'm going to keep this talk fairly high level, so we're not going to get into the details of this. I just want to make sure that you get the sort of the broad components of these ideas that go in to make these technologies work. So this is called conflict-based search. It's a two-level search algorithm. By search, I mean, you know, things like A-star search, that sort of heuristic search frameworks, right? So why do we call it conflict-based search? Well, first of all, let me illustrate what's going on here, right? So we are considering here let's say there's a blue agent that starts from this location, right? So this is a little environment map just used for illustration. A little blue agent starting from there needs to get here, right? And then a red agent starting from there needs to get there. Suppose they individually plan their paths, right? I mean, so the blue agent goes from here to here, here to here, here to here, here to here, and then the red agent traverses this path. Well, at time 2, they're colliding in this location. They're both going to be in that location. If they planned independently their shortest paths, then they would realize that there's a collision there, right? Now, once we realize that there is a collision there, of course, all this is being done this is not being executed yet. This is still in the planning phase, right? So paths are planned independently for the individual agents. And then if there is a collision, right, then what we do is we try to resolve this collision. Well, this collision came about because, both the red agent and the blue agent happen to be in the same location at the same time. So in order to resolve this conflict, there are two possibilities. Either you reroute the red agent, preventing him from being in that location at that time, or you reroute the blue agent, preventing him from being in that location at that time, right? And then once you reroute the red agent now has to find a new path, right? So, but he's not allowed to be in that conflicting location at the conflicting time. So you see, it's a two-level search algorithm. Because of the high-level search tree, what is going on is that we are in the business of resolving conflicts. But in the low-level search tree, which is just a single agent planning problem, because we're just rerouting the red agent on this side. Here, we are just rerouting the blue agent, right? So it's a single agent planning problem on the low-level search tree, but under the spatiotemporal constraints that are recorded by the high-level search tree, right? So like this, we have split up what is exponential time computation in the high-level search tree and what is polynomial time computation in the low-level search tree, right? And there are several benefits of doing this, but one thing that I want you to notice right away is that this is not a search conducted on the space of assignments. It's a search conducted on the space of conflicts, right? What do I mean by this? Because, one way to have looked at this problem could have been, I enumerate all possible paths for an agent going from point A to point B, right? And then now I have to choose one path for each of these agents from their set of possible paths such that no two of them collide. Well, this is not a feasible approach. The reason why this is not very good is because even for a single agent, the number of paths that can go from point A to point B could be exponential. So just enumeration, even for single agents, is not a good idea, right? So therefore, in conflict-based search, each guy plans an independent path, all right? So they don't have to enumerate all possible paths ahead of time. They're just planning independently. And now if there's a conflict, they're in the business of resolving these conflicts. Okay, so
Satish, there is one quick question, if you're okay to take one question here.
Sure.
There is a question around how did the NP-hard problem become polynomial time? If you can talk about that for a couple of minutes again.
No, the NP-hard problem did not become polynomial time. What happened was that I split the exponential computation that's required into the high-level search tree and the polynomial time computation that is required into the low-level search tree. The exponential time complexity is still there. The high-level search tree is still going to be exponential. But it's good to have clarity about what is the exponential phase and what is the polynomial phase instead of clubbing all of them together. Yeah, does that answer?
I see. Solving a sub-problem, is it, to make it polynomial?
It's not really a sub-problem. Sub-problems are structured differently. This is more in the, there's a high-level search tree, and every high-level search node imposes restrictions on what can go on in the low-level search.
I see.
Yeah, but the low-level search is polynomial time because it's about rerouting a single agent, right? Whereas the high level is about resolving conflicts between multiple agents.
Got it. Thank you.
Yeah, and in general, when someone declares NP hardness, right? Well, not everything is lost, right? Because after all, NP hardness is associated with a class of problems. There is still something that we can extract out of the instance-specific structure, right? And then when we talk about instance-specific structures, then good practical algorithms are all about automatically identifying the structure in that particular instance and making use of it. So CBS, for example, is one of those algorithms that actually identifies instance-level structure automatically and exploits it. Now, for example, I mean, here are some bullet points, right? I mean, why is this a good algorithm? Well, the two-level search procedure segregates. We have clarity on what is polynomial time computation and what is exponential time search effort. The path finding at the low level is polynomial time. Conflict resolution at the high level is still exponential time, right? However, because this is all about resolving conflicts, then we are automatically in the business of exploiting independence. Imagine two agents that are operating in very distant parts of the environment. They don't need to be, talking to each other that much. They could be fairly independent, right? I mean, so where do we draw the line of independence? We don't explicitly do it. We create the framework such that it automatically exploits any such independence, or in general lose interactions, right? And then, so that's one benefit, that automatically there's an exploitation of independence and loose interactions. The second benefit is that once we cast things in the framework of heuristic search, then all kinds of wonderful heuristics can be used, right? When people who have studied A-star search algorithms know that how powerful heuristics can be. So both at the low level and the high level, we can use very clever heuristics. I'm not going to go into the details of what these heuristics are, but they're very clever heuristics, right? And not only that, I think in your bachelor's degrees, you might have studied something called A-star search, but we also have a generalization of that called focal search, right? In our group also, we have worked on focal search. I mean, focal search uses two heuristics instead of one, right? I mean, so there's a primary heuristic that just like it needs to be admissible and consistent to guarantee optimality and everything. But there's a secondary heuristic. So that doesn't need to have admissibility and consistency, but can also powerfully enable the search, right? So in the focal search framework that can be done both at the high level and the low level, we can get huge gains in efficiency, and we can also create a framework where we can trade off a little bit of optimality for huge gains in efficiency, right? So it's a frame. So the A-star search algorithm is always going to give you optimal solutions, but the focal search algorithm, you can specify whether you want the optimal solution or let's say very close to the optimal solution. So it's a bounded suboptimality framework. But if you say you want, close to optimal, very close to optimality, then it can give you this leeway for improving the efficiency of the algorithms by a large margin. So it's a way to trade off solution quality against efficiency, right? So these are the benefits of the conflict-based search approach. There are an entire lineage of algorithms based on CBS, enhanced CBS, improved enhanced CBS, and a ton of these algorithms exist. But I'm just giving you the vanilla flavor here. So do we have another question at this point? Or? All right. So
yes,
yeah,
we do have one interesting question. It's actually not really a question. It's a summation of what has been said. So I'll just read it out just in case we missed out on something. So planning both together equal to an NP-hard problem. Planning a single agent equal to a polynomial problem.
Yeah.
We need to reduce planning both together. So we use conflicts here to inform the planned single agent path rather than calculating every single path simultaneously.
That is correct. Yeah. So we are not planning on the joint space of assignments. We are planning on the space of conflict, so to speak. It's a conflict resolution. So, there's in general, when we talk about optimization problems, right, there is this thing where every problem, particularly for those who are coming from, an operations research background, there is something for every problem. You also have the dual of that problem, right? So it's almost like working in the dual of this problem, conflict resolution space. Okay. All right. So one thing to notice here is that although the conflict-based search algorithm solves the problem that is NP-hard but uses certain assumptions, it is the thing that is doing combinatorial heavy lifting. Okay, so let's consider this simple example to illustrate the point. Suppose there are two robots here, 1 and 2, right? And then they need to get into target locations where in the target locations, they're in the reverse order. So 2 needs to be here and then 1 needs to go there. Well, if you think about it, right? I mean, so it doesn't matter what the kinematic constraints on these robots are. It doesn't matter what their maximum velocities are, accelerations are, and all that, right? None of this matters. The critical thing to observe is that the only way that they can achieve that configuration is for robot 2 to go here, slip into the alleyway, and then let robot 1 pass, and then robot 2 comes and pops up back again and goes back to his spot, right? But this critical intermediate configuration is what is key here. But that critical intermediate configuration I could have figured out even by making the assumptions that I just did. I didn't need to factor in all the kinematic constraints to realize that this is the intermediate configuration that we need. All right. So that is why the combinatorial heavy lifting is going through the CBS framework. So now let me show you once again this video here. So we use the AI solvers only to the extent that they are recognizing the critical intermediate configurations that the robots need to go through so that everyone accomplishes their target locations. I'm happy to reinstate the kinodynamic constraints after I do this, right? Okay, so now let's look at the next video. You can ignore the first part here. We still have to talk about it. Okay, so but you see what we are doing here is that the first thing that we are solving looks very toyish, right? It is just about agents moving with uniform velocities and getting into intermediate configurations and so forth. It is not about real robots. But the point is that we are able to do this for hundreds of robots very efficiently, right? Including like in the Skiva system, where end to end they have to exchange positions through narrow corridors, where it's very easy to get deadlocked otherwise, right? Because the corridors are narrow. Okay, let me stop this here again and then continue. But please understand that this is where the combinatorial heavy lifting is being done. Okay, now let's look at the robotics perspective, right? Okay, from the robotics perspective, well, we need a little bit of background here, right? I mean, just so that we can reinstate some of the kinematic constraints that we had ignored, okay? So, so this is the framework of simple temporal problems that is used very routinely in intelligent scheduling, right? So just to give you an example, so this is about someone planning their day's events. X0 here, which is traditionally set to the beginning of the world. In this case, the beginning of the day, which is 12 a.m. So someone is allowed to sleep between 6 and 8 hours, and then breakfast between 1 and 2 hours, and then there's a travel time for 1 hour, and then they are allowed to work for anywhere between 2 and 5 hours. And then they have lunch for between 1 and 2 hours. There should be a gap of at least 5 hours between the breakfast and the lunch, and they should be done with their day's events by 4 p.m. Right? I mean, so seems like a reasonable set of constraints. Well, how do you figure out a schedule that satisfies all of these constraints? Well, if you notice the nature of these constraints, they're always difference constraints, right? Because that's the nature of when you constrain one event against the execution of another event, then you're always creating a difference constraint. You will never have something crazy like 7x1 plus 4x2 is less than 17 or something. It's always the execution time of one event minus the execution time of another event that is between some interval. That's the nature of temporal constraints. All right. So given this, we can actually solve them very efficiently using a graph theoretic reinterpretation. So what I do is, since every constraint is, well, I mean, even if you look at the nature of one of these constraints, right? I mean, the execution time of one event minus the execution time of another event is between a lower bound and an upper bound. That actually compiles into two separate constraints, right? So it's less than U and greater than L. Now, the thing that is about greater than L is actually another difference constraint. So it's tau xj minus tau xi is less than U. And in the reverse direction, it's tau xi minus tau xj is less than minus L. So the fundamental constraint is really a difference constraint. So the execution time of one variable minus the execution time of another event is less than some W here, right? I mean, that's the fundamental unit of a constraint in temporal reasoning problems. If I represent that as an edge, right? So I put an edge from xi to xj annotated with w, right? To encode the constraint that the execution time of the head variable minus the execution time of the tail event should be less than or equal to w, the weight that's annotating that edge. Now I can translate constraint by constraint. I can give them a graphical representation like this. All right. So this is called as the distance graph representation of the simple temporal problem. Now, one amazing mathematical property of just this representation, right, is that a consistent schedule, meaning that, a schedule that satisfies all the constraints exists if and only if there is no negative cost cycle in this distance graph. So in other words, the absence of negative cost cycles actually tells you about the feasibility and the consistency of the temporal constraints in the scheduling problem that you just gave me, right? And then if indeed there is no negative cost cycle, which means that the simple temporal problem is consistent, then actually the STP admits a class of solutions, not just one solution, right? In general, it admits a class of solutions. And I can give you two specific solutions where we can assign the earliest start times to every event by setting his execution time to the distance, to the negation of the distance from that event to x0. Remember that x0 is a special variable that represents the beginning of the world because we need a frame of reference. And so assigning to every time point to every event the execution time that is equal to the negation of the distance, the shortest path distance from xi to x0 will satisfy all the constraints. Similarly, there's another schedule where you give the latest start times, where you can assign to every event the execution time of the distance from x0 to all these variables in this distance graph. Now notice that in this distance graph, it's a directed graph on the one hand, and the second thing is the edge weights could be negative, right? So you cannot use the Dijkstra's algorithm here. You have to use the Bellman-Ford algorithm to compute the shortest path distances. Is this point clear that, generally if you have temporal constraints of this nature, then you can solve them in polynomial time, not just by giving them to a linear programming solver or something, but simply by encoding it as a graph and then using shortest path computations in the graph. So many times, shortest path computations are particularly useful, not just because they literally represent shortest paths, but there are many other problems in AI that don't necessarily come on a silver platter looking like a shortest path problem. Temporal reasoning problems are standard examples of this, but they can be easily converted to shortest path problems, right? Okay, so this is our background knowledge before we reinstate the kinematic constraints, okay? So what I do here is that once I have my environment graph, right? I mean, the environment on which I'm doing my multi-agent pathfinding problem. So S1 needs to go to G1, the agent sitting at this location needs to go to G2 and so forth. So I use my AI solvers like CBS to generate a discrete solution. Notice that this discrete solution was generated just to recognize the critical intermediate configurations that the robots have to go through. They were not realistic in terms of execution because they were ignoring all the kinematic constraints of all the robots, right? But it is still doing the heavy lifting of the combinatorics here. So if I get a valid discrete solution, now it'll say, okay, robot 1 needs to go from A to B, B to C, C to D, D to E. All right, that's the schedule. Whereas robot 2 needs to go from B to C, C to F, and then back from F to C, and then go from C to D. Right. So if this is a valid solution, then then an agent cannot be in the same. I mean, two different agents cannot be in the same location at the same time. All right. But now I want to take this thing and then I'm going to convert this into a temporal plan graph, pretty much like a simple temporal problem, right? Because after all, what is a discrete solution telling me? It is telling me how each robot should traverse from his start location to the goal location, right? And it's also telling in which order they should cross intersections, right? If two agents happen to go through the same location, to the same intersection, in which order should they do this, right? So it's coordinating in that way as well. So what I'm going to do is that I'm going to take each of these robot schedules and simply write them down as traversal edges in this simple temporal problem, right? And so the superscript here is the robot 1, right? And then the subscript here is the time step. So robot one is going from A to B, B to C, C to D, E to E, the traversal that is recommended for him via the discrete solution. And then same thing I lay it out for robot two. But then what about these cross edges? These cross edges are just encoding, the coordination constraints here, right? I mean, whenever I see two locations that are repeated both for one robot and for another robot, then I have to draw precedence constraint between them, saying that this robot needs to be in B before the robot one is in B, because that's what the discrete solution recommended anyway, right? So I'm going to draw this precedence edge between them here. I'm going to mark these little circles just to create a little bit of safety distance between the robots. But basically, the idea is to draw precedences between agents when they're crossing the same locations. So I can take my discrete solution and represent it as traversal edges and precedence edges in a temporal plan graph, right? So I can convert it into simple temporal problem. But what this simple temporal problem also allows me is that now I can start accommodating kinematic constraints. For example, if a robot has a maximum velocity and a minimum velocity, then I know that one of these traversal edges, right, which is of a certain length, then I will need at least the length by maximum velocity amount of time, and at most length by minimum velocity amount of time. Now, slowly I have reinstated the velocities constraints on the robots, right? And I know that this framework can be solved in polynomial time as a post-processing for the discrete solution that I got from the AI solvers. If I want to reinstate richer kinematic constraints, right, something about, let's say, maximum acceleration capability of a robot or something, then I will have to combine the framework of simple temporal problems with this thing called Bezier curves. Once again, for people who have seen Bezier curves in other contexts, right? I mean, they might be familiar with this, but in general, I just want to mention this without going into the details, right? I mean, Bezier curves have been used for any number of applications, right? I mean, so they have three very interesting properties. So the one of approximation, meaning that, any curve can be approximated by Bezier curves using an appropriate number of control points. This is the so-called Weierstrass approximation theorem. And then closure, meaning that the derivative of a Bezier curve is another Bezier curve. And then convexity, which is a Bezier curve lies entirely within the convex hull of its control points. These properties are important from a robotics perspective because let's say you want to put a maximum acceleration constraint on a robot, right? Because that's related to force and the force on the actuators. Then what you do is you represent the distance covered by distance covered as a function of time by a Bezier curve. And then the first derivative of this, which is talking about the velocity, is another Bezier curve because of the closure property. The second derivative is another Bezier curve because of the closure property again. And then you want to restrict this at all points of time to be less than some maximum value. All you need to do is that the control points of this second derivative Bezier curve, you just need to restrict each of them to be less than this maximum. And you can be assured the entire curve will lie within that. This is by the virtue of convexity. So like this, I'm not going to the details of how to combine simple temporal problems with Bezier curves, but I just want to mention it for now, avoiding the complex mathematics. But there's a point that I want to make here, a broader point, right? You see, in robotics, what really kills you is not so much generation of plans, but it's execution monitoring. Let me explain what I mean by this, right? So when we actually plan for a team of robots, it's one thing to come up with, how they should coordinate with each other and all that, right? I mean, that itself is a hard task, but the AI solvers at least can do it under a certain number of assumptions. But then the thing is, when they actually start executing this, then we are in trouble because, execution is not perfect. Things may fail, things may accumulate error. And, the moment you deviate for the first time from the intended behavior of the plan, then suddenly you're questioning yourself. Should I start replanning? Right? I mean, because first of all, I need to estimate where I am. And then even if I do that successfully, should I replan now? I mean, but by the time I replan, because planning itself is fairly expensive, something else has changed. And now that plan is unviable, right? So now it becomes a very vicious loop. right? So there is this debate about whether we should do plan generation, where we assume perfect execution, right? And then we have to go through expensive replanning if this assumption fails, or we do policy generation. Policy generation is different. Policy generation means that you already have pre-calculated a response for any situation that you get yourself into. You don't have to work under the assumption of perfect plan execution, right? But the issue with policy generation is that it's too expensive compared to plan generation. It is significantly more expensive. But what we have introduced here is an STP framework, where we need to generate the plans. Like in plan generation, it's a very feasible thing to do as a one-time thing, right? So we generate plans, and from that I just went through how to generate a corresponding simple temporal problem, right? But now is the interesting thing. At the time of execution, when there are going to be deviations from the intended behavior of the plan, then we don't need to do replanning, because any minor imperfections that are there are simply absorbed. Because remember that a simple temporal problem doesn't have just one solution, it has a class of solutions. So even if a specific solution has failed because of deviations from the current, from the intention of the current plan, then you can always quickly regenerate another one from that class of solutions, because simple temporal problems can be solved in polynomial time. So in a polynomial time resolving phase, you can absorb all these imperfections in plan execution. It is
Can we
only
take a question?
it is only when there are significant deviations from the intended outcome of the plan, then replanning is necessary. All right, I think we have a question coming here.
Yes, Satish, if you're okay to take a question,
Sure.
it's primarily between, before we go to the STP framework, people, I mean, the questioner understands what the plan generation is,
Yeah.
but what is policy generation? Like, if we can explain with the difference between those two. Yeah.
Yeah. Policy generation means that, you're generating, you're already foreseeing the conditions that you could get yourself into. It's almost like, think of it, it's typically done in the MDP framework, right? I mean, the Markov decision processes, which means that, you are, let's say you're executing something and then something happens, right? Then you recognize what is it that happens, but you don't need to replan. You already have a pre-calculated response to it. That's what a policy generation is. Does it make sense?
I see.
You have a
It's more like
pre-calculated response.
reaction to the observation.
Correct.
Yeah.
It's more like a reaction to the observation, yes. But those are very hard to generate. I mean, people try to do them in an MDP framework, but those are much harder to generate than plans.
I see. And then your work is coming up with an STP framework, which solves the problems in both these methods.
Well, I mean, technically neither of these methods, right? Because what we do is we just generate a plan just as a one-time thing, right? Like plan generation does that. That's very feasible to do. But then the way we address imperfections in plan execution is not via being ready with a response, but via creating a computational framework where the response is a polynomial time resolving phase. It's not the exponential time replanning phase. See, replanning will take, because planning and replanning are pretty much the same thing. Replanning is hard, but resolving the STP. Remember that the STP has a class of solutions, not just a single solution. So there are many solutions in that class that are still viable, right? They can be retrieved in polynomial time. You don't need to go back to the very beginning of this problem, right? I mean, you have, because all the causal interactions, all that reasoning you have done, and you have created this temporal plan graph. This temporal plan graph has cleverly taken a discrete solution and converted it into a class of actually feasible executable plans, a class being the keyword here, right? But then once something happens, you don't need to backtrack and change all your causal interactions all over again. You just need to backtrack to the point where the particular candidate that you've chosen from this class of feasible solutions is now recomputed, but that's just a polynomial time algorithm.
I see.
Yeah.
Thank you.
Sure. So now actually let me show you the benefit of doing it this way, right? Because that'll actually give you very good execution frameworks, right? So let me just show you another video. And remember that, robotics, it's really execution monitoring that gets you. It's not really the planning, right? So now I'm going to show you a video where you can see the power of imperfections being absorbed in the STP framework in a polynomial time absorption phase, right? And we can do this with so much precision that now we have three kinds of things going on. There are the ground robots, and then there are these two kinds of quadrotors. And then you will see one quadrotor actually landing on a ground robot, right? And they're getting to various configurations. All this because, notice first of all that the obstacle environment is very complex, right? So the problem by itself is very complex because there are rich obstacle space. They have to fight gravity. There is not much time for deliberation, and then they have to avoid collisions with each other. The downwards effect is there, and they have to do it the most efficient way and get into configurations and with high precision, one landing on the other and absorb all the imperfections in plan execution, right? So let's take a look at it. Okay. All right. So let's get back to the presentation and
Yeah, that's very encouraging to see because everyone has to negotiate all the obstacles to reach from the source to the destination, and reach there safely and securely.
yeah.
And you also had a global perspective and a local perspective of one one drone's perspective as well. So that's very amazing.
Yeah. I mean, so this is really a very good case study in how addressing the problem at different levels of abstraction and creating principled solutions for each level really makes the difference, right? So yeah. All right. So
If I may, Satish, one small question.
yes.
If you could, just reiterate the different levels of abstraction that we have passed through till now.
Yes. So
Yes.
one we looked at it as a complexity theory problem, and then from not a complexity theory problem. I'm sorry. We looked at it from the perspective of a complexity theorist. We declared its NP hardness, right? And then it was bad news, but then that's the point when the AI guy would come in and still salvage it for us by exploiting instance specific structure, right, and creating the CBS framework. And now, but the AI guys makes a ton of assumptions, right? I mean, there's he ignores all the kinematic constraints and the various kinds of things that could happen, the imperfections that could happen at the time of executing the plan. So under all these assumptions, but he still does the heavy lifting of the combinatorics to recognize the critical intermediate configurations that robots have to get into in this coordination phase. And then after that, it's a post-processing thing via the STP framework, right? This is where the robotics guy comes in and reinstates everything, all the kinematic constraints. He can easily do that in the STP framework, at least for the max and min velocity constraints. But then the richer kinematic constraints, I mentioned how we can use Bezier curves. It's something that is more mathematically involved, but it's essentially conceptually the idea is still the same, right? The benefit of doing it this way is that we have created an STP framework which now represents a class of problems, right? I'm sorry, and the STP framework, which represents a class of solutions. All these are kinematically feasible. They're just they have the same causal interactions, meaning that they have the same crossing orders on the intersections and everything. But within that, as far as that causality is fixed via the discrete solution, there are tons of kinematically feasible solutions that still admits. And we are ready to explore that space in polynomial time just by recomputing shortest paths. Right? I mean, so that's why we can absorb the imperfections in just resolving the STP instead of replanning and starting all over again from the causal nature of this problem. Yeah, I mean, one abstraction level that I ignored for now is the physics level, right? The reason is because then it gets the story gets very long, right? I mean, so the physics guys usually come in when we're talking about a very high level perspective on where the idle robots should be hanging out in anticipation of future demands into the warehouse and things like this, right? Then they become things like, okay, concentration equations, how should you pair up the tasks with the robots and all this, right? I mean, that level I will ignore for now. Okay.
Another question, Satish, is there is this huge swarm of robots that you're talking about.
Yeah.
Be it drones or be it robots on the floor.
Yeah.
Is it I mean, are your algorithms more distributed in nature where the compute and the intelligence is all in the nodes? Or is it a central system sending instructions to all these?
Yes. So what I've shown you here is that the planning is centralized, but the execution is distributed.
I see.
But
Awesome.
but based on this, there are other frameworks that one can create. I'm just giving you the vanilla flavor of everything, right? I mean, so. But
Yeah,
what I've told you for now is the planning is centralized, but execution is distributed.
Gotcha. Thank you.
Sure. So I'm just going to remark a few things before we move to the next topic here, because I already mentioned CBS, right? I mean, it's not the only place where conflict-based search is used. In fact, we ourselves have used conflict-based search for network slicing. What does network slicing mean? It is, basically when you have to create virtual networks on the physical infrastructure. Like, because changing the physical infrastructure of the internet is very hard. It's very resistant to architectural changes. Whereas on the other hand, just by flexibly commissioning resources from that physical infrastructure to create virtual networks. For example, all of us are in a virtual network right now, right? I mean, how should we intelligently allocate resources from the physical network to different virtual network requests, right? So that there's maximum utilization of these resources. That also can be done via conflict-based search. And in fact, we are the state of the art by a fairly large margin in network slicing as well. We are also working with the Linux Foundation to convert these academic algorithms right now to the real world transition. So that's one remark. The other remark that I wanted to make was about intelligent scheduling, right? I mean, I introduced simple temporal problems and everything. Once again, those are vanilla flavors of how to do scheduling. One can talk about scheduling in a much broader way, where you can talk about, let's say, appliance scheduling, right? I mean, so where we have all kinds of constraints between when appliances should be switched on and switched off, and how they should coordinate with each other. For example, the dishwasher needs to run only after the rice cooker is done. All these kinds of constraints are there. And we can talk about energy minimization, where the cost of a unit amount of electrical energy is actually varying throughout the day. So so this is actually a realistic picture from the Southern California Edison company for the cost of a unit amount of electrical energy, how it varies throughout the day, right? So from midnight to 8 a.m., the cost is different. From 2 p.m. to 8 p.m., the cost is something else. So now there is, how should you come up with a schedule that satisfies not only all these constraints between them, but also minimizes the total amount of energy consumed, such that the energy, the unit price of energy itself is changing throughout the day, right? So These kinds of problems can also be solved, interestingly enough, in polynomial time. They're complex algorithms that use max flow arguments and all this, but our group is also one of the leading groups for doing intelligent scheduling. All right, so this is another remark that I wanted to make. A third remark that I wanted to make is simply because we spoke about Bezier curves and a framework that we created called differential programming, where you see we can convert differential equations into constraints of a linear programming problem or a quadratic programming problem. So, one partial differential equation at a time, right? We parse it and convert it into a constraint on the control points of the Bezier curve that represents those functions participating in those differential equations. And we get a compilation into either a linear program, not always is this possible, but there's certain classes of differential equations where this is possible, that you can compile them into linear programming problems or quadratic programming problems and solve them in polynomial time, building up this equivalence between analytical techniques for solving PDEs and programmatic solutions for solving PDEs. But the good thing about the programmatic perspective is that inequalities come for free, right? I mean, so you see in mathematics and analytical methods, once you have inequalities, in robotics, you always have inequalities because you have something about the maximum acceleration, right? I mean, it's a bound on the acceleration, the second derivative of something. So if you convert that into a linear programming formulation, then this inequality comes for free because the operations as solvers allow for this. The other thing is that decision variables come for free, right? Meaning you could add extra decision variables into your substrate of the partial differential equation. So now you see this actually creates a very interesting reasoning framework for decision variables and differential equations. Traditionally, whenever decision variables and differential equations have come together, the way we have solved problems is based on simulation. Let's say that there is this smart building example where we have logical constraints that talk about which room should be which meeting can be scheduled in which room. We have possibilities there and restrictions there, and when should a meeting be scheduled, we have possibilities and restrictions there. And so you can imagine a whole bunch of timetabling constraints just in the realm of logical variables. But then on top of that, you could also have differential equations, because now you need to maintain temperatures in the meeting rooms, right? So if a meeting is going to happen in a certain room, it needs to start heating or cooling according to a differential equation. And you need to do, so now you have an interplay of logical variables and differential equations. And the question is, how can you do this in the most energy minimized way, right? And so the traditional approach has been for every possible consistent value for every possible consistent assignments of values to the logical variables that satisfy all the timetabling constraints, you simulate the differential equations and see what it gives you, and then you pick the one that's most suitable for you. But this requires simulation. Simulation is expensive. But what our approach does is that everything is compiled into an operations research substrate, right? Like a linear programming problem or a quadratic programming problem. And then we solve it significantly more efficient. All right, so there's a paper on this. I won't go into the details again, but something as an interesting side remark. The other remark that I want to make is about, since I've also worked in NASA domains, is that you see, in NASA domains, there are the Cassini-Huygens project, for example, right? I mean, I'm not saying that I worked on this. I'm just saying that, I've worked on NASA problems. In fact, my Stanford PhD dissertation was really motivated by the problems that were coming from the NASA domains, because I'd done a couple of summer internships there. But I'm just giving you the Cassini-Huygens project as an example of how AI systems are required, right? I mean, so this was a spacecraft. I think it was a joint collaboration between NASA and the European Space Agency that took off from Earth in 1997, right? And then after huge odyssey after hurtling through space for 7 years, it reached the vicinity of Saturn. And then once it reaches the vicinity of Saturn, it needs to slow down. Otherwise, it will overshoot the gravitational pull of the planet, and then the spacecraft is lost forever, right? So now, the question is, these critical actions of slowing down and everything, right? They need to be done in windows of opportunity. And the window of opportunity that we have for doing this is really just about 2 hours. If you miss it, then it's essentially gone, right? So, and we do not know what might happen in these 2 hours. Almost invariably, because we haven't been there. It's the first time we are venturing out into that space. We don't know the conditions. Something might fail, right? And then if something fails, how do we reconfigure ourselves from there, right? So the there is no point of trying to control it from the ground stations because light itself takes more than 2 hours to reach the vicinity of Saturn. So the idea, therefore, is to move the intelligence on board, right? So first of all, we need to, if something goes wrong, we first of all need to identify what is it that went wrong, right? I mean, so this is a diagnosis problem. So that from that state, we can either do replanning or reconfiguration of some sort. So I want you to understand that even in such complex domains, it is important to peel the complexities of the problem in the right abstraction levels and in the right modularities. So some of the heavily used technologies in NASA domains are actually intelligent scheduling and the planning and the planning sort of technologies, right? So automated planning and scheduling are very relevant to these domains. There's a little bit of model-based diagnosis and so forth. So please don't think of it as, an end-to-end, because, people these days think of everything from the machine learning hammer. That's not the case, right? There are many other areas in AI, and ultimately it all boils down to understanding the problem at the correct abstraction levels and using the correct algorithmic techniques that are applicable at that level. All right.
Just seeing a common thread here, Satish. So every single problem has a common set of abstraction layers, or from a mathematical perspective, one can really see there are certain kind of problems that can be put across domains. You solve a robotics problem, it's not really a robotics problem, it's a graph theory problem. And so that's been a big takeaway from all the discussions here. And I want to ask if you'd like to say something very specific about the importance of how a research student should look at and analyze the problem in different abstraction levels and not just get in a domain specific problem.
Yes, because you see, the thing is, there are quite a lot of different domains out there, right? And different communities working on their kinds of problems. But what is interesting is not just the problems that a community works on, but it's also the kinds of techniques they have to address the combinatorics there, right? And these are the techniques that if you begin to understand, then they could be applicable to pretty much other domains as well, at least the abstraction layers of other domains as well. So for me, a community is interesting, not just for the problems that they work on, but also what kind of tools they have, because combinatorics is there in every domain, right? And across different abstraction layers of that domain, different kinds of optimization techniques will be useful. And these, could come from other communities as well, right? So that's the takeaway that I want everyone to know, that it's really branches of the same tree. But the tree that we're talking about here is one of addressing combinatorics and algorithm design. Yeah, does that make sense?
Yeah, that makes sense. Thanks.
So it looks like we are significantly running behind schedule. So what do we do about the time? Can you say a little bit?
There are a few interesting questions that have come up. So one of the reasons why I asked a specific domain-related question is some questions are very specific to the domain, right?
Yes.
How about using neural operators, depot nets, and
I think we should avoid this overly domain-specific question. I mean, I'm happy to answer them, when if they reach out to me personally, right? But that's not the point of the presentation that I'm for now, right? Because actually, I might have to skip the entire discussion on FastMap and the study on nanoscience, and we should get to really this part, which is the interesting part about how to delve yourself into higher education and research, right? And how to do a PhD and how to be a successful researcher. But let me actually stop um, at the place where this one, algorithms and AI from a combinatorics perspective, right? So all right, so a ton of things we did not cover, but I'm happy to share the slides later on so that people who are interested in this other topics can take a look at them as well. So okay, so the perspective on AI and algorithms is essentially this, right? Think of the capability of artificial intelligence as, you know, the ability to build these large houses, right? Beautiful buildings with all the great architectural designs and everything, right? But the algorithms as the actual bricks and the building blocks that go into them, right? So, you know, if you were to build another building, which is of great architectural design as well, and if you're simply fascinated by the architecture of a building and you know nothing about the building blocks, then you're not going to go far with that, right? On the other hand, if you know about the building blocks, right, and you can be always inspired by the architecture of a building, you can build grander things. All right. So creativity and novelty really come from a proper understanding of both the architectural aspects of it as well as the building blocks of this. So please do not ignore, you know, your algorithms courses, right? Because they are the ones that help you adapt into an ever-changing scientific world. The other thing that I also want to mention that I put in red here is one of leadership. Now, what do I mean by this? It's actually a critical point. Well, you know, I'll say this in the most appropriate words. For anyone who takes an interest in geopolitics, right? A lot of geopolitical angles come from the producers of technology, right? Setting the narratives for the consumers of technology, right? So, you know, if you look at, therefore, AI as the future of power or something like this, then you probably need to be on the producer side. And if you need to be on the producer side, you need to invest in algorithms as well, because that is when you know about the building blocks. You can be inspired by other AI systems and create grander ones. If you do not do this investment in algorithm side, you will always be you know, just using technologies, right? And the narrative is set by someone else. So this is another key point. It's subtle, but it's a key point. All right, so I'm gonna have to, in the interest of time, you know, unfortunately skip over FastMap, which has tons of applications, and the case study in nanoscience. But I will get to this higher education and research because that's really about what it's about the audience. All right. So any questions before we get to this part here? I mean, other than the really, really domain specific ones, right, which we can take offline, but generally in terms of, you know, the importance of algorithms or any such thing.
So one thing is very clear to the audience right now is that the level of abstraction that needs to be put into the framework of thinking of problem solving.
Mhm.
And now the next question comes, how do I prepare myself to set a framework like that in my mind when I get into a graduate program or get into my projects?
Yes, yes. Well, so in one way, right, the art of feeling the complexities of the problem in the right order it requires a little bit of experience, right? And obviously that comes from understanding many different sort of algorithmic tools that have been developed by different communities, and knowing that for what kind of combinatorics, what kind of algorithmic techniques are going to be relevant. But in general, you know, although that part comes with experience, I can tell you how to get there, right? I mean, so in other words, for example, if you're thinking about a PhD, then you know, I can tell you some of the things that you should keep in mind while you're doing a PhD. Or if you want to build a research career in general after a PhD, how to do some of the things to keep in mind being a good researcher as well. Okay, so how to do a successful PhD, right? Is that a reasonable answer, Rahul, for now?
Yes.
So, okay, so how to do a successful PhD? I'm sure many of you have this question in your mind. Well, should you do a PhD, right? I mean, first of all, that's largely a personal choice, right? I mean, I have nothing to say there other than this is a personal choice. But I can also mention that in terms of, as a society, fostering PhD programs are really good. Although at a personal level, it's really your choice. But I'm saying from the level of a community, I think we should foster PhD programs because that's where science advances, and it's good for the scientific advancement of a nation as well as the entire world in general, right? Okay, so now assuming that you have decided to do a PhD, some of the things to keep in mind. First thing is learn everything in challenge mode, right? This is important, but this is not to be confused with becoming a difficult personality. That's not what I mean, right? I mean, I'm saying you have to learn to question everything and accept it only after you challenge it, right? So actually there are two outcomes of this. One thing that could happen is that you prove yourself wrong, right? When you learn something new, you challenge it, you think about it, and then you prove yourself wrong. That's actually a great outcome because now you also know what is wrong, right? Because because there's a lot of wealth of knowledge, not just in knowing what is right, but also what is wrong, right? I mean, so that's beneficial. Occasionally, you prove the textbook wrong, right? And then you happen to be right. Well, in that case, also it's a great outcome because you go and write a paper. And so try to do everything in challenge mode. That's one thing. The second thing is that you see PhD programs are a little bit different because up to the level of your master's degree, what has happened is that you have a standard formula for success, right? You take your courses, you do well on the projects, and you're disciplined and hardworking and everything, you get good grades, it's done, right? But the PhD program is not about discipline, right? You need something else more than discipline. It's about obsession. Discipline is still required for the execution of your ideas, to work out all the details, to write the paper in a way that the broader community can understand it, to maintain a certain level of perfection, and all that, right? I mean, so all this is great from the discipline angle, but you need the obsession factor for creativity, right? Because without obsession, you don't really put two and two together, right? At least not the totally creative parts of it. Huh? And then the next thing to keep in mind is to go solo. I think this is one mistake that several students do, which is they think that, when they, at the beginning of their research careers, they need to associate themselves with, let's say, a senior student or a faculty member, and then work with them to learn more and everything. Yes, you can do that. Of course, you can learn from them, but you have to learn to take ownership. You have to go solo. Identify a problem that you are completely responsible for yourself, right? And not simply depending on components of it being solved by others. The reason why this is important is because now you develop problem-solving skills at every level, right? From the ground level of code level optimizations to the high level of, what is the big picture of this, right? So once you understand problem solving skills and all the issues that come up at every level, then you are able to speak the language of everyone. That's when the collaboration floodgates open up. You don't reverse engineer this, right? So collaboration floodgates, you don't go seeking out, they should be imposed on you simply because you know the issues at every level. So please go solo, right? I mean, and take responsibility. So that's another thing. And then the another key thing is do not compare yourself to others. This is also very important because you see, like I mentioned, in the up to the master's level, because the formula for success is the same, then one can feel okay, they put in this much amount of hard work, they're entitled to this much amount of grades or rewards or something like this. All that is fine up to the master's degree, but in the PhD program, what happens is that there are too many uncontrollable factors. The biggest mistake you could be doing is to compare yourself to others, particularly in terms of rewards, right? Because your situation is so circumstantial right? It depends on what topic you're working on, what university you are at, what is the relationship between you and your advisor, right? All these dynamics come into play, and some topic today might be hot, but 4 years later it may not be hot anymore, right? And then suddenly all these years that you invested in this, now you're not being rewarded for it anymore. Now you'll feel that injustice is being done to you compared to the other guy and all this. All these are real killers, right? So please, first thing you should do is stop comparing yourself to others once you enter the PhD program, right? And invest in algorithms courses is the next point. See, it's okay to be a domain expert. In fact, it's even important that, when people think of a domain, that your name comes up all the time. That's definitely the case. But you should not be just a domain expert. You should retain the capability to adapt, right? And this you can do only if you have the portal for communicating with other communities. And every community offers combinatorics to you. That's the real portal. So if you invest in algorithms, then you're in good shape to adapt. All right. So, and especially in a rapidly changing scientific world, please, while you can be domain experts, don't be just domain experts, right? Retain the capability to be good in algorithm design, because something changes, the market forces change, you can adapt, right? And then the other thing is try to learn in peer groups, right? I mean, not just from the instructor. I mean, ideally, you can find other students or something that you do joint learning with. The reason is because many times your peers will tell you the wrong way of thinking about things. And there's an enormous amount of knowledge in knowing what the wrong way to think about something is, right? And you also develop different perspectives on a problem, right? And one more thing is to talk about your research frequently. Even if you're solving a small problem, talk about it to others, because what happens is that usually the other person doesn't get you, right? Because they're not in your field, right? I mean, they don't necessarily get you. So over a period of time, because you talk more and more about your research, you will learn to use the right choice of words to convey your research ideas to them in easier and easier ways. This is also very important from a communications perspective. If there is one thing that discipline really should fetch you in a PhD program, it's the ability to write. Please make that a habit, because this is one thing that is really a matter of discipline. You will have to write a lot as a PhD student. And so this one, like setting aside a time every day to do writing, right, is a very important habit, because it actually increases tangible output. Right? Because unless someone sees tangible output from you, could have very nice ideas in your head, but if you don't write them down, no one will reward you for it, right? No one knows about it, right? And when you write things down, you have to be very precise, use short sentences, because English is inherently an ambiguous language, right? So the ability to create short sentences, and if required, to combine math and English, right? I mean, so as to create these very precise sentences. So please make writing a habit. It will improve over a period of time. Even in the beginning, if you don't write well, scientific writing is different from writing a novel or something, right? So so it will improve over a period of time. And in any case, as a PhD student, you will have to do a lot of writing. The other point is that there is no perfect topic, right? Once again, this is something that PhD students often think that they will have to wait for the perfect topic and then they're going to do this wonderful dissertation on it and everything. Well, it happens very rarely, I would say, right? I mean, moreover, the PhD program is not about the perfect topic. It's really just a certificate for you. It's a capability certificate. Right, that you're capable of doing research, right? It's not the only piece of work that you will ever do, right? So there is no point in waiting for the perfect topic, especially no point in wasting 1 or 2 years in the PhD program, right? So please keep this in mind, because especially because these days funding directions really dictate the kind of topics that you can work on. So they come with certain constraints. So there is no such thing as a perfect topic. So don't waste your time over that. Instead, it's just a certificate that you have to go and, sort of work your way to get this one. And then, depends on what life throws at you. Maybe you will get to work on more interesting topics later. Now, having said this, I'm not suggesting that you do a flimsy dissertation. That's not what I'm saying. I'm just saying just don't wait for the perfect topic. But whatever topic you work on, you have to treat it with full respect and make an impact on it, right? So in other words, you should become better than your advisor by the time you finish your PhD on that topic, right? You should be the go-to person even 10 years later. That's the intention of doing a PhD program. You become better than your advisor on that particular topic, at least, right? Because in the being in the business of creating the next generation of scientists, we would fail if the next generation was not better than us, right? I mean, that's the point of academia. That's the point of a PhD, that you become better than your advisor, right? And then the other thing is you gather secondary publications. Now, this is what do I mean by secondary publications? Is not low quality publications. That's not what I'm saying. Secondary publications here refers to that the publications that are not necessarily in your dissertation topic, because after all, you are going to identify some topic and carve out a dissertation out of it, right? Something, it's more like a direction, right? Which is not just 1 or 2 papers, but maybe, even 10 years later, this activity in this field. That's what a reasonable dissertation topic is. But then on the way of doing this, pick up topics by collaboration with students from your advisors, other students from your advisors group, or whoever else it is, because you talk to other researchers in a university. Pick up secondary publications that are even not necessarily related to your dissertation topic. The reason is because if the market changes tomorrow, then you can pivot, you can advertise yourself on the secondary topics as well, right? You have multiple ways to grow from there, right? So, and of course, just working on different topics, of course, always is beneficial, because you just become more knowledgeable and you accumulate a better tool set. And then one more thing is make use of the full resourcefulness of a university. It's not just you come in and then, you stay in your program, just listen to your advisor, and then, 5 years later you graduate and go away. That's not the point, right? I mean, the advisor-student relationship is there, of course, right? But it's also about making the full making use of the full resourcefulness of a university, because a good university has the top names in pretty much every department, right? So even if you're a computer science PhD student, you can connect with the physics department. There are top names. They're easily approachable, right? So you can do relatively free spirit things, right? And you should definitely make use of it, build a network. And the most important thing is you have to have your heart in it, right? Because this is not a profession where you can treat it as a job, right? You need an obsession factor. You need to have your heart in it, all right? Any questions before we go to the how to be the last 2 slides about how to be a successful researcher, which is beyond the PhD program?
There is one question, but I think you've already answered it, but I just say it out loud again. Would you recommend doing a PhD without masters?
Oh, there's no problem with it at all. In fact, like I have a master's degree, but I was never enrolled in the master's program, right? Because we got it on the way of doing a PhD, right? I mean, so if that possibility is there for you to enter a PhD program without a master's, I mean, so be it. I think you actually save time that way.
The whole focus is to get the research mentality in hand, not
Well,
just to a degree.
yeah, the research mentality, it's just really about the points that we went over, right? I mean, you have to learn things in challenge mode, right? I mean, and in some sense, like I said, I mean, the research mentality is probably another name for the obsession keyword here, right? I mean, so you obviously need a good tool set, but you shouldn't necessarily always go with the flow, so to speak, right? Because the current directions in research, they themselves are being set by funding directions. They're not necessarily, I mean, funding directions dictate a lot. in what kinds of research topics become hot and so forth, right? So meaning that, if you're always going with the flow, essentially you're going with funding directions. You should have the courage to go in other directions as well, right? Which you feel are of more scientific value, right? So all these contribute to the research mentality. Yeah, Rahul.
Yeah, that'll be great. Thank you.
And then how to be a successful researcher. Just a few key points here beyond that of a PhD program, right? Like for example, if you're a starting young faculty member or somewhere, right, or leading a team in some other place, so please keep an open environment, right? The reason why this is important is because hierarchies do not work well in science. They might work well in other professions, but not in science. Because in science, it's always easy to check who is correct and who is wrong. It's not always the boss who is correct, right? I mean, you can go to the blackboard, just work it out, who is right and who is wrong, right? So it's much better to have internal criticism than external criticism, right? I mean, it's much better to work it out in a group without a hierarchy, figure out all the issues, and then you publish your paper, right? Because if you do not do this, then one day someone else sitting in some other country points out an issue with your paper. That's not going to go down well. So it's much better to have internal criticism than external things. For this, you need to have a healthy, flat structure in your group as opposed to hierarchies. In fact, you really make students productive if they feel that they can become like you, right? I mean, that not because you're their boss, but they can become like you, right? I mean, so if they get that feeling, they will actually be much more productive. And then the point that I just mentioned, you have to be a bold, objective thinker. It's not always necessary to go with the flow, because going with the flow, there are many things that happen behind the scenes. And many times, organizations are in an arms race with each other about certain technologies, and many times, there are funding directions that that dictate what is going to be considered hot and what is not. So we cannot, as researchers, yes, I mean, we are sort of constrained by these things, but we should not be following them all the time, right? I mean, we have to be essentially free thinkers internally, right? And we have to be bold when we do this, right? I mean, because that's really what creates the groundbreaking research in the long run. And then the other point is that you have to develop the art of pitting the complexities of a problem in the right order, right? I keep saying this because it's a really important thing, right? I mean, because every community offers a certain way of thinking, right? It's not that you want to import techniques from the other community as a black box. That never goes well, because, you're not going to, if you understand things only as a black box technology, right, you will understand it the wrong way anyway, right? You will end up using it the wrong way because you don't really know the nuts and bolts of it. You don't know the real capabilities of it. And if a problem comes along where, it's slightly different from the technology that you have at hand, you don't know how to modify it to make it applicable, right? So always understand the nuts and bolts, which is why I keep saying about this building blocks, which is understand the combinatorics and the algorithms that go from it. And they could be coming from different communities, but don't take technologies from them just as a black box. You can use it for convenience after you understand the nuts and bolts, but not without understanding the nuts and bolts of it. And then the other thing is that it's really about intensity, not competitiveness, right? So this is also a key thing to keep in mind, because the reward structure that we have created for researchers is that they obviously get rewarded with more publications and everything, but it's very tempting to think in terms of competitiveness, that we need to have more publications than another person or something like this. But if you try to do that, then once again, it's not in the spirit of science, because then you will go after relatively low quality publications, and then and then we cannot trust the results anymore, because there are certain kinds of papers where I'm not even sure whether these results are correct or not, right? So it becomes a huge game there. So please do not think in terms of competitiveness. It's about intensity. Intensity has nothing to do with others, right? Whereas competitiveness is all about how to be better than others, right? I mean, so if you are intense just in your own right, and it's just the relationship between you and the curiosity that you have for science, then as a product of that, as an outcome of that, you can become competitive. But once again, don't try to reverse engineer this, because then you get into all sorts of games, right? And then encourage collaborations and team building, right? I mean, by this I mean, you have to do it the right way. I actually had a case study for this in nanoscience, that you have to collaborate on problem formulation first, right? Because what problem formulation gives you, because you see, the thing is, you take two scientists, who are experts in different areas, you try to get them to communicate with each other. Actually, they do not do it so well, right? I mean, they're individually experts in their own domains, but bringing them together and making them work on something interdisciplinary, it's not very easy. But if they can learn to talk the language of combinatorics, because every area has combinatorics in it, if they know how to talk the language of combinatorics and collaborate on problem formulation first, then it opens up both of them. Then the communication becomes much easier. And we had a very interesting use case in nanoscience for how we did this, but in the interest of time, we couldn't go over it. And the other thing is, use a bottom-up approach, right? What I mean by this is that, you see, for example, if I were to collaborate with another faculty member, I'm busy, he is busy. It's okay, we are going to take out 1 hour of our times to meet with each other. Not much comes out of it. It is much better to do this bottom up, meaning that get your students to collaborate with their students, or you personally go and talk to their students, right? There is no harm in doing this, right? Like I said, hierarchies are not the right thing here, right? So in fact, probably the PhD students know much more of the details, and they will tell you much more than what their advisor will have time for, right? I mean, so use bottom-up approaches. They work very well, right? And then other point is that, you see, it's okay to guide students and basically write papers with your students. Essentially, your research directions are evolving according to the capabilities of your PhD students and their own research interests. All that is fine. I mean, it's okay. You should have your own agenda as well, right? I mean, on top of your students' agendas. But although most of your papers can be with your students, right, you should always retain the ability to go solo. That you should never give up, right? Because I actually have a friend from Australia, a very big name in his field. What he does is that he has plenty of students, and he's a very prolific researcher. But what he does is that every year, 1 or 2 papers he's going to write single authored. He's going to do everything himself, right? The code level implementation, the experimentation with it, the paper writing, everything, so that he keeps honing his problem solving skills at every level. Repeatedly, you should put yourself in a position so that you go solo on many of these things, right? Because that will keep honing your problem solving skills at every level. And then make scientific writing a habit. I mean, I cannot emphasize this enough. This is the one thing about science that is really a matter of discipline, right? That you get your tangible output only via writing, right? And then use short and precise sentences, because, like I said, many languages have ambiguity in them. So you want to keep it short and very precise. It's almost like, after you factor out the intuitive parts of your paper, the rest of the paper should be compilable by a computer. It should be that precise, right? So pseudocode, precise arguments and everything, right? And there's a certain amount of perfectionism that you have to maintain, even at the level of English and the level of style, right? Because, even a comma being in a different font, right? You should look at it, right? The reason is because once you have this level of perfectionism, when it goes through a review process, it's obviously, as a reviewer, it puts you in a certain kind of positive bias if everything you see is perfectly written, right? So humans are humans after all, right? I mean, so the ability to produce perfect work, especially in our profession, is very important. No? And then be rigorous with arguments and proofs, right? I mean, this is also important because sometimes, you're proving a theorem or something, and then you say, okay, but by a symmetric argument, such and such a thing. Well, I mean, is it really symmetric? I mean, don't trick yourself into proving things that are wrong, right? I mean, this is also because this has happened, right? And then people get into very embarrassing situations after that because someone else sitting in another country is catching this error that was published in your paper, like 5 years ago, and now you have to explain everything, right? So don't let this happen to you. Be very precise about theorems and proofs, right? And really work out the nitty-gritty details of this, and provide everything necessary to replicate your results, right? This is also in the very spirit of doing science, that replicability is important. So anything that you do, lay out the pseudocode for it, theorems and proofs, and as far as possible, I mean, of course, there are some cases where data is private and everything, that's a different matter, but as far as possible, make everything open source that someone can replicate your results as well. And then make scientific speaking a habit as well, right? Giving a speech is very different from writing, right? I mean, there are two different ball games. So on the one hand, when I say in scientific writing, you have to be very precise. In scientific speaking, right? Like, let's say I give a conference presentation for 20 minutes or 30 minutes, it's completely the reverse formula, right? You should avoid the mathematical details, because after all, in 30 minutes, you cannot go through the math. I mean, even if it's a highly technical audience, the math is coming at you too fast, right? I mean, so you cannot flood them with all the math in that limited amount of time. So instead, your speech is just an advertisement for your paper. It's right. I mean, so you purposefully keep it intuitive, but you always have the backup formal results in your paper, right? And use more pictures and less text, because pictures much more easy to understand than text, right? I mean, who's going to sit there reading text, right? I mean, so use pictures in your presentations, use intuitive arguments, just intrigue them enough that they are now incentivized to go back and read your paper, right? It's not about presenting the full details of everything. You have worked out the details. If someone requires it, you're happy to give them the paper, but the talk is not about that. The talk is about an advertisement for your work, right? And then properly balance funding directions and academic directions. This is where certain personality traits come in as an advisor, right? Because funding directions is one thing. I mean, nothing moves without funding. It's understandable. But on the other hand, they should not 100% dictate your academic directions, right? In the history of science, a lot of interesting work has come which was not necessarily funded, right? Someone who was just inspired by science, right? And also sufficient freedom is required for your students to really blossom. So you have to know how to balance these two, right? And the same thing that I said for a PhD student as well, you should have your heart in it. Otherwise, you're in the wrong profession. Right? So with having said all this and having skipped over half of my talk, I will conclude here with giving contact details about how you can reach me. You can just go to my website if you want any of my papers, or I'm probably lazy enough not to put up all my papers there, but at least they'll tell you what the titles of these papers are, and then you can always Google them, right? So that's one thing. And then if you need to reach out to me either for the questions that you had now and I couldn't answer because they were too in the interest of time, because they're overly domain specific or something, they can always reach out to me. And if you have a very personal situation about relationship, your consideration of a PhD program or something, relationship with your advisor or something like this that you don't want to speak out here, you can also reach out to me for that reason as well. So having said this, I will conclude and hand it back to the moderator for any further questions.
I mean, that was one eye-opening session, to be very honest, Satish. And obviously, it's got right questions being asked from the audience too.
Mhm.
One question that has just come up is, thank you so much for this talk.
Mhm.
A personal question for you. How did you find your obsession in this?
Well, Well, you know, since it's a personal question, I will also answer it at a personal level, right? So I didn't. I was always clear. I would say probably from the age of 3 that I wanted to invest my life in science, right? I mean, I never had a question about it in my mind. I don't know what exactly it was, where it was coming from, right? I never said I wanted to become this or that in terms of profession. I always said, even as a 3-year-old, that I wanted to be a scientist. Now, I wasn't really sure what kind of science it would be, right? But my commitment to science was very clear from the very early stages of my life, right? But in general, I think, you know, just the ability to have a free mind, that you know, that you're a free thinker, right? Once you're a free thinker, a really courageous one, right? Then I think automatically science will intrigue you, right? And then you could get into it. Is what I feel. But you know, I don't want to speak on behalf of others, because in my case it was more of a you know, it was very, like I said, it was from childhood days. But I also suspect that you know, if you're a free thinker in general, right, then I think science will intrigue you in some way or the other.
Thank you for that answer, Satish. A few takeaways just to conclude.
Mhm.
The framework of problem solving, how to build that skill of peeling different layers of abstraction.
Yeah.
That's a skill that comes from practice. And
Yes.
a PhD program, there's a certificate program that helps you develop that skill. And at
Yes.
the same time, while we are focused on our problem, might as well collaborate with others within the same university, network with others as much as possible.
Yeah.
Build in this collaborative way of working so that you develop a broad framework of problem solving, and
Yes.
that sets you for a successful researcher life.
And the
And
ability to not compare yourself with others, right? Because
absolutely.
that is very important, because you know, the moment you feel that, you know, something, you're not being rewarded for something, then you lose motivation, right? Because if you think in terms of reward, right, and comparison to others, it's there are too many uncontrollable variables in this profession for things to go right. So
Absolutely. And I hope all the viewers here today who have joined us, and also the ones who would be watching this later on at a convenient time back in India, you would have further questions. Feel free to reach out to Satish directly. His mail ID is pkskwork@gmail.com. And keep the obsession going on. And hopefully we've done a good job in inspiring you to be obsessive. Thank you so much, Satish, for your time. We overshot a little bit. It's not a little bit, but you definitely have so much to offer, and we should definitely plan for a follow-up session with you in the future.
yeah, well, you know, so we overshot a little bit with just half of my talk. So,
So I'll just hand it over to Vikas for the final concluding. I mean, Vikas is always smiling. Thank you.
No, I think that was fascinating and inspiring. People who will watch this video will be inspired with all the advice towards the end. But having said that, you know, thank you for everyone who joined us today and will be watching in the future. Thank you, a huge thank you to Satish and Rahul as well. Just remember this session is recorded and will be shared on Spotify and YouTube. Just a heads up for the next session. The next session is on Web3 technologies and decentral technologies, and I will be sending out an invite for that. And yeah, thanks everyone for joining. That's it for today. Have a very good weekend. Bye.
Thank
Thank
you.
you.